Now you might need to get your chips out again, your black and red chips, because we're going to talk about in this next video the idea of this black and red chips model. We're going to start playing with these black and red chips or tiles. And it's crucial that we think of the black chips as +1, and we think of the red chips as -1, right? So you've got these squares or these circles, whatever they might be. And again, black is +1, red is -1. It can also be helpful to think about it like money. Each black chip is a $1 credit. Each red chip is a $1 debit. And when you think about it like that, and the combining of the chips, every single integer can be represented an infinite number of ways. I'm going to jot that down. Every integer can be represented an infinite number of ways. So here is a really good example, very simple example of that. So take a look at these three different sets of chips. The one on the left has 3 black chips. So example A has 3 black chips. So it would just have 3 positives, right? And that's it. We can see it has a value of 3. If we look at the second one in the middle, example B, we have 4 black chips and 1 red chip. Well, if we combine those and say, what's the true value of it? What you'll notice is that when you pair up a black and a red, they cancel each other out and have a value of 0. So what you're looking at is then, well, what's left? Well, 3. So those would have a value of +3, the leftover stuff. Same thing happens here. Now we have 7 total chips, but 2 of them are red. And so these 2 red will cancel out with these 2 blacks, right? So we would have +5 and -2. And the total value would be, again, +3, the leftover ones. And so you start to see, again, that statement I wrote above, every integer can be represented an infinite number of ways, as long as we just keep adding 1 black and 1 red, the value is still going to be 3. And that's a really important concept when we start to use this model of black and red chips. So you try with your chips, see if you can come up with 4 different ways that you could represent the number 0. So 4 different ways to represent 0. Just try it. Take a moment. Again, there are an infinite number of ways we could do it. We could do it with 4 black and 4 red. We could do it with 1 black and 1 red. We could do it with 3 blacks and 3 reds. We could do it with 6 blacks and 6 reds. It doesn't matter, right? Or that's 7, sorry, 7. As long as there's an equal number of black and reds, it's going to have a value of 0. So this is where we sort of get into the idea of addition, okay? So what we're going to do in this next picture is look at a very specific addition problem, -5 + 2. So again, this uses symbols to represent the idea of numbers, and now we've got negative numbers included. And so let's see what the model using chips might look like. When you are adding, you're thinking about it in terms of sets. We have a set over here on the left and a set over here on the right, and we're going to add them. We're going to combine them together. And so you can see the 5 negative chips, the 2 positive chips. And when we add them, we're combining them all into this one big set. But then what we have to do is determine the value of that set. As we saw before, every black can be paired with a red, and we look at what's left over. And you can see that there are 3 red chips, so that would be a value of -3. So let's try one that looks like this. I'm going to give you the addition problem, and you see if you can determine what the diagram would look like. What is the model for that? Take a moment. -4 plus -3. Well, hopefully you put down something that looked like this. -4 is represented by 4 red chips. -3 is represented by 3 red chips. And we're, again, combining them into one big set. What's the value of this? Well, there are 7 chips. They're all red. So that has a value of -7. So -4 plus -3 is equal to -7. This is a really good one to help students see that, again, when you're adding numbers, adding integers with the same sign, you make more of them. Sometimes I see adult students, well, students of all ages, think that that might become positive when you are adding negative numbers. But no, you can see here that we're not, right? You just get more negative. It gets more negative. And so what we start to see are some rules that come about from addition. And so let's take a look at what those rules might look like. If we could write out in words what we're learning here. So the rules for addition of integers can be summarized here. Let A and B be positive integers. So negative plus negative equals negative. So that's one of the rules. -A plus -B. Right? And when we say that let A and B be positive integers, that sometimes trips people up because then they see this and they're like, well, isn't A a negative integer right there? No. This sign right there is saying we are going to take whatever A is and make the opposite of it, right? So if A is a positive integer, if A is 7, then when we write this, now it represents -7, okay? So it is important that we start with this assumption. A and B are positive integers, and then we're putting those negative signs in front of those variables here. So -A plus -B is going to be negative of whatever the sum of A and B would be. You can see this, -3 plus -7 is equal to negative, or the opposite of 3 plus 7, which is -10. Here we have a positive plus a negative. And notice that we have 2 of those, positive plus a negative, and a positive plus a negative. Well, then there are conditions set in at the end of this. This equals a positive if A is greater than B. So if A plus -B, if A is a bigger integer than B, then it's equal to A minus B. You can see that here. 15 plus -5 is equal to 13 minus 5, which is equal to 8. If you think about that in terms of your chips, maybe use your chips to prove that to yourself. For number 3, we have positive plus a negative equals a negative if A is less than B. So A plus -B is equal to negative, the opposite of B minus A. 6 plus -11 is a good example of that. And then negative, that's going to equal negative whatever 11 minus 6 is, which is -5. This is a tricky one, I think, for people to just memorize this, but you can start to make sense of it over time. And this is a really helpful one if you have to add or subtract, which you may on your competency test, really big numbers having to do with integers. For example, if you had to do 47 plus -63, that would be a hard one maybe to figure out, how do I write that, right? How do I stack that? Am I doing 63? Am I doing 47 plus -63, right? There's not a great way to do that. So what we actually do is you look at just the 47 and the 63, you subtract them almost in the opposite order. That's the B minus A. You find that as a difference of 16, and then it's going to be a -16. So it's almost like we switch the order of these, we subtract them, and we make it negative. A lot of people say when you're adding a positive and a negative, you just find the difference between the two numbers in whatever order you need to do it, and then you take the sign of whichever one was bigger. So in this first example, 13, if you just look at the A and the B, 13 is bigger than 5. So we know our answer is going to be positive. In this one, 6 plus negative 11, 11 is bigger than 6. And since 11 was negative, the answer is going to be negative. And if you go back and play with the chips a little bit, you'll start to see that, right? In this second scenario, we end up with more red chips than black chips. And we just find the difference between those two numbers, and the answer is going to be negative. So the chips really do help us see that. Another way that we often can show addition of negative and positive numbers is with a number line. And so I've got two showing on here. So the first one is the addition -5 plus 3. And we always start at 0 when we do these. And so then we first go to the -5, and that's this arrow here. And then we're going to add +3, which takes us back to here. And this is our ending point. This is a little more abstract, I think, than the chips, but it does help with the thinking of which direction are we going on a number line? Are we getting bigger? Are we getting smaller? For the second one, we have 7 plus -4. So again, we start at 0, we're going to 7. And then when we add -4, that means we have to go backwards 4, because it's like adding on a debt, and we end up at +3. So this is also a useful tool when we're trying to envision adding and subtracting with, or adding with negative numbers. So let's move into subtraction now. That was all addition. Let's now talk about subtraction. This one could get a little bit more challenging. And so one way we might consider this, depending on the scenario of our integer problem, is the takeaway model. We talked about that before. The idea of picturing subtraction as taking away. And we might have a problem that looks like this. -6 minus -2. And so get your chips out. And if you get your chips out, you're going to lay out a set of 6 negatives. And then when we are, so that's this part, right? That's the -6. That's our starting point. We start with that many. This symbol means take away, if we want it to. That's how we want to picture it. And then we're taking away this many negative chips. And since they're all red, we have 2 negatives that we can remove. So we take those out and we see what's left. And we can see that it would be -4. I always, again, like to think about it in terms of money. If you're $6 in debt and somebody takes away $2 of your debt, you're less in debt. You're only $4 in debt now. Some older learners that might resonate with them a little bit more. So this is where we start to get, maybe gets a little more challenging. So I'm going to write the problem down. Let's go -6 minus 2. -6 minus 2. And so I want you to play around with this for a minute. See if you can figure out what this might look like and how you might go about modeling this with your red and black chips. Go ahead and pause and then try that. So I'm going to show you this with my own model. Now remember, I don't have the black counters, I have yellow ones. So we start with -6. So you can see I have 6 red chips out. Well, the problem said we had to take away 2, but the 2 was not a -2. It was just a regular old 2, a +2. If there are no +2s there, positive chips, no black chips there, or in my case, yellow, how do we take any away? Did you figure out that one thing you can do is put in what I like to call a 0 pair? a red and a yellow together, or a red and a black together, have a value of 0. Remember, we started this conversation that every number can be represented an infinite number of ways. So if I take those 6 tiles, the red ones from the very beginning, and I just put another red and yellow together, I didn't change the value of my set. It still has a value of 6. And I can do it again if I want. By adding another red and yellow, or red and black, we still have a value of 6. What you see on my screen has a value of 6. Now we can do the action of taking away 2 positives because we have them. So now I'm going to just remove a yellow and remove another yellow, or in your case it would be black. And what we end up with is, in front of us are 8 red tiles, -8. And that's what you see here. If you like to think about it in terms of debits and credits, if you start off $6 in debt, and then somebody takes away $2 more from you, now you're more in debt. Now you're $8 in debt total. So that idea of a 0 pair can be helpful. So now let's take a look at one where we do 3 minus 5. So we're starting with a positive 3, and we're going to subtract 5. So you think about how you might go ahead and model that with the red and the black chips. So one way you might do it, like we did before, is something like this. Actually, let me just post this picture here. So if you start with 3, right, you always think about, what am I starting with? 3. That's what we see here. But then we have to represent 3 in a different way. We have to represent it in a way that allows us to take away 5 positive black chips. How do we do that? We add a red and a black and another red and a black. Now we have 1, 2, 3, 4, 5 blacks that we can remove. They go away. What are we left with? 2 reds. So we can see through physical manipulation that 3 minus 5 is equal to 2. So often in math, we have to change the way one number is represented into another representation in order to do the thing that we want to do. So another way we can think about this is adding opposites. It's another way that subtraction can be represented, is through the addition of opposites. Okay. And so let's do actually that same problem, that same idea, 3 minus 5, but we're going to represent it in a different way. The action of taking away 5 black chips actually has the same result as adding the opposite of 5. Take a minute to examine that. 3 minus 5 can also be represented as 3 plus -5, 3 plus the opposite of 5. And so if we wanted to model this with chips, it could look like this. Start with a representation of 3 that looks like this. We have 1, 2, 3, 4, 5 black tiles, 2 red tiles, so that has a value of 3. Now, why did I start with it looking like this? Because we are going to add 5 negative tiles to that set right here. When we combine these two things, what we end up with are 5 black tiles and 5 red tiles all paired together and then taken away. And what we're left with would just be the 2 red tiles, the 2 negatives. And so this is thought of, again, as I'm starting with $3 but I'm adding on $5 of debt. So instead of thinking about it like taking 5 positives away, you can think of it as adding 5 negatives to your pile. And so that's what the idea of adding opposites is. And actually, that's how we often define subtraction of integers. Take a minute to review this definition. For any two integers, a and b, it doesn't say positive, it just says any two integers. A minus b, meaning you're subtracting them. Again, they might be positive, they might be negative. As long as we are subtracting them, then we can rewrite a minus b as whatever a was, plus, we're going to change this minus sign to a plus sign, and then we will take the opposite of b. And so we have to be careful, though, because the opposite of a positive number is a negative, but the opposite of a negative number is a positive. So let's practice this just a little bit to end this video. So what we're going to do is I want you to try to rewrite this subtraction problem as an addition problem, thinking about it like what we did right here, and then compute it. So we will start with 15 minus 7. So we'll start with trying to rewrite it as an addition problem. I'll do this first one with you. 15 minus 7, if we rewrite it as addition, is 15 plus the opposite of 7, which is negative 7. The solution to that would be a positive 8. The next one I want you to try is this. Negative 14 minus 3. Take a moment and see if you can first rewrite that as adding the opposite. So we always keep the first number the same. We change the minus sign to a plus sign, and then we take whatever this number was, which is a positive 3, and we take its opposite. Now it's negative 14 plus negative 3. This might take you back to our very first example, when we took red chips and added them to more red chips, and now we have even more red chips, negative 17. Often, this is an easier problem to understand or visualize than this one for some people. Now let's try this one. This is where they can get a little tricky. Take a moment, examine that, and try to do the same thing. Again, we start with negative 2. That's our starting point. We are changing our minus sign to a plus sign. And then we're taking the opposite of this number. Notice that this number was a negative number, and the opposite of a negative number is a positive number. Notice how subtracting a negative here really becomes a addition here. And now we have negative 2 plus 5, which is 3. This generally is going to be something that people have a better understanding of, an easier way to picture in their mind than what we started with there. So that gets us through addition and subtraction with integers, and hopefully you have a better understanding of how you can model those, especially with those red and black chips.